Hello everyone and welcome to another Physicalculus video. Today I'm going to be solving a forces problem for you guys, but specifically a forces problem involving calculus. So I'm going to assume that you know a little bit of calculus before solving this problem. So this problem is adapted from chapter 5, problem 81 in the university physics textbook, and it says, you are standing on a scale in an elevator whose velocity is varying with time according to the expression v of t equals 4.0 meters per second squared t plus 1.2 meters per second cubed t squared. Your mass is 70 kilograms. What is the reading on the scale at t equals 3.4 seconds? So we have a velocity function v of t. So we know that we're going to need to take a derivative at some point to get to the acceleration. But first, let's list our givens, draw a picture, and all of that. So we have our elevator, and this is our scale right here, and this is you or me, one of us, and it's moving upward according to a velocity function v of t. And we know that v of t, which I'm going to write down here, is excuse me. We know that our velocity function v of t equals 4.0 meters per second squared times t plus 1.2 meters per second cubed times t squared. And we need this constant to be squared and this constant to be in meters per second cubed because if you plug anything in for t in seconds, then you will just get meters per second and meters per second for each of these terms, and therefore you'll be able to add them and get velocity at that time. But we don't want that. We want acceleration, so we're just going to leave it for now. And it says our mass is 70 kilograms. And we want to know the reading on the scale at t equals 3.4 seconds. And we know that g equals 9.81 or 80, so I'm going to use 0 actually. G equals 9.80 meters per second squared. And Fg, the force of gravity, which we will have in our problem, equals mg. So let's draw a free body diagram for the moment when t equals 3.4 seconds, right? Because that's what we're looking for. So at t equals 3.4 seconds, here's me on the scale. And we're going to have the force of gravity pulling down at us with Fg equals mg, right? And we're going to have the normal force from the scale on us at t equals 3.4 seconds, so which I'm going to call n. So what are we looking for in this problem? Well, we're trying to find the reading on the scale, right? And that's reading our weight. And essentially the weight that the scale displays is how hard it detects that it needs to push up on you to counteract the force of gravity. So at t equals 3.4 seconds, you're moving up according to this velocity function right here. And so the scale is going to have a specific reading at that point different from the other readings because the velocity and therefore the acceleration varies. So we're looking for instantaneous acceleration. We're going to need that in our problem, but our target variable, what we're solving for, is n, because we're looking for the force that the scale thinks it needs to exert to the force that the scale needs to exert to counteract the force of gravity. So n then is our target variable. Sorry, let me change the focus real fast. Okay, so now that we know we're solving for n, what is n at t equals 3.4 seconds? Well, to find n, we need the acceleration at t equals 3.4 seconds. And this is where the calculus part comes into play, right? Because we have v of t, which is varying with time, and we need to get to a of t, specifically a at 3.4 seconds. And to do this, we need to take the derivative of v of t, right? Because dv dt equals a. So dv of t dt equals a of t. So let's take the derivative of this velocity function here. So a of t equals dv of t with respect to t. So this is d dt of 4.0 meters per second squared t plus 1.2 meters per second cubed t squared. Alright, so to take a derivative, all we need to do, especially of this one, because this one's really easy, all we need to do is put the coefficient of the variable that we're taking the derivative with respect to in front of the coefficient and subtract 1 from that. So subtract 1 from the superscript. So this will give us a of t equals 4.0 meters per second squared, and t goes away because there was just one of them here, plus 1.2 meters per second cubed times 2t, because we have t squared, so the t goes down in front, and we subtract 1 from the superscript of this t. Alright, so this is our expression for acceleration. So now what is it at 3.4 seconds? Well, all we need to do now is plug in 3.4 seconds for t. So we have this equals a at 3.4, which equals 4.0 meters per second squared plus 1.2 meters per second cubed times 2 of 3.4 seconds. Alright, so let's just real quick before we calculate this, let's make sure that our units are going to be correct with dimensional analysis. So we have 4 meters per second squared here, which is good because we need our units to be in meters per second squared, so this term looks good. And then this one, well, we have 1t here, so that's just going to give us seconds divided by this seconds cubed, so that's going to also give us meters per second squared. So that's good. That means we can add these two, and it means our acceleration at 3.4 seconds is going to be in meters per second squared. So that looks good. Alright, so let's calculate this here. Alright, so I got 12.16 meters per second squared at t equals 3.4 seconds. So this right here, 12.16 meters per second squared, is our acceleration at 3.4 seconds. Alright, so we have our free body diagram, we have our expression for acceleration and our value for acceleration at the time that we want. So let's find an expression for the normal force now, because that's what we're solving for. So applying Newton's laws, specifically Newton's second law, we have the sum of the forces on a given object equals mass times acceleration of that object. So if you can see here, if this is my, I'm just going to call this my positive y direction and my negative y direction. In our positive y direction, we have n, right, the normal force, which we're solving for. So n, and then in the negative y direction, we have Fg. So this is going to be minus Fg equals mass times acceleration. And we know that Fg equals mg, as labeled here and here. So n minus mg equals ma. And we're solving for n. So we can add mg to both sides. Add mg to both sides plus mg. And this is going to be equal to n equals ma plus mg. And specifically, this is going to be equal to n equals ma plus g, right? Because I can factor m out. And in our case, it's going to be n equals m times a of t plus g, because acceleration is varying with time. Alright, so this is our expression for n, and we have a of t, specifically a at 3.4, we have g, and we have m. So we can solve for n. So this is going to be n equals m a at 3.4 seconds plus g. Alright, so one more time, let's conduct dimensional analysis to make sure n is in the correct units. So g is in meters per second squared. A we've already figured out is in meters per second squared, so we can add these two terms. That's good. And this is going to be multiplied by the mass, m, which is in kilograms. So this is going to give us kilogram meters per second squared, which is in Newton, which is exactly what we want in our answer because we're solving for the normal force. So this is good. This looks like the correct expression. So let's plug in some numbers here. We have n equals 70 kilograms as given to us in the problem. 70 kilograms times a at 3.4, which is 12.16 meters per second squared, plus 9.80 meters per second squared. Alright, let's calculate this real fast. Alright, so after performing this calculation, I got 837.2 newtons. And this seems like a reasonable answer, right? Because we have 70 kilograms, and it's varying with time, and specifically it's going to be 12.16 plus 9.8 at t equals 3.4 seconds. So we know that the force that the scale reads at this time is going to be greater than if you were going to be standing on it normally, because the elevator is accelerating upward at that specific time, and therefore essentially it's going to be pushing up harder on you than it normally would. So this seems like a reasonable answer here. And rounding to rounding to two significant figures. This is going to be 840 newtons. We need two significant figures because each of our values given to us in the problem are in two significant figures. So 840 newtons is our answer for the reading on the scale at time equals 3.4 seconds. And yeah, that is how to do this problem. Thank you guys so much for watching. I'm trying to grow my channel, so please subscribe and like if you did like this content, if it was helpful for you. Even if it wasn't helpful, I appreciate you watching anyway. Please, if you have any questions or you've caught any mistakes that I made, please correct those and ask those questions in the comments down below. But please guys, be respectful. I'm only human, and everyone else, every other user on this platform is only human as well. So please be respectful, please be kind in the comments. And yeah, thank you. I'll see you in the next video.